Good morning, welcome back. So, we will start the discussion on inverse kinematics today. In the last few classes we talked about the forward kinematics starting from the coordinate transformation matrix and how do we go to identify the DH parameters, and then using DH parameters how do we get the transformation matrix and then use it for forward kinematic analysis. And we saw few examples in the last few classes and see how to use the forward kinematics for getting the position and orientation of a manipulator that can be expressed as a function of the manipulator parameters, the joint parameters as well as the link parameters. That is what we discussed. So, today we will start the inverse kinematics problem. I briefly explained to you what is inverse kinematics problem. So, we will see the details of this problem and how that can be solved for manipulators. So, what we going to cover in this is basically the problem definition. So, we will try to define what is the inverse kinematics problem all about, and then we will see something called solvability. So, it is not that necessary that always the inverse problem can be solved. So, it can be solved under certain conditions only. So, we will see the existence of solutions and then the problem of having multiple solutions. So, some cases there will not be any solution, in some cases there will be multiple solutions. So, we need to see what is that solvability, and then we look at the solution strategies. There are different strategies to solve this. So, we look at the closed form solutions as an algebraic or geometric solution, and then we look into the then there is another method called the numerical solution. We will not go into the details of numerical solution, just for to tell you that also is a method for solving inverse kinematics, but we will be talking only about the closed form solution. And then we go into the velocity relationship. Of course, that is not the inverse kinematics part. So, we will look into the velocity relationship, that is the relationship between the joint velocities and the tip velocities. There we discuss about the Jacobian and singularity, and finally we will talk about the statics also. So, the force relationship under static conditions. So, that is going to be the discussion for the next few classes. Now, we already mentioned about the inverse problem. What is the manipulator inverse problem? As you know, the manipulator tasks are normally formulated in terms of the desired position and orientation. So, as I told you, so I have an object here, I have an object here, okay, this is an object. Now, I have a coordinate frame assigned to this object, so that I know the relative position and orientation of the object with respect to the base of the robot. Now, my interest is to see how can I use this robot to pick this object from here. I need to pick this object from here and place it somewhere here. I want to place it somewhere here, and I know this position also. So, I can define this position where I want to reach. So, I have this object in this position and I want to pick up this using this robot. So, if I had to bring this tool to this position, what should be my joint angles is the problem in inverse kinematics. So, that is the way normally all the manipulator problems are formulated. So, in knowing the joint angle and get where will it reach, the forward kinematics is useful, but not in the practical scenarios like this. Here we are interested to know what should be the joint angles to reach here, and similarly what should be the joint angles for the tool tip to reach here, to drop this point object here. So, that is what is the requirement in the practical application. So, that is what says that they are normally formulated in terms of the desired position and orientation. So, we have a desired position and orientation for the tool, and we want to know how can we reach that position and orientation using the joints, and that is the inverse problem that is of interest to us. So, we have something from here to pick and then place it somewhere else. So, how to reach these positions are the interest to us, and a systematic closed form solution applicable to robots in general is not available. That is, this problem cannot be generalized, because each robot will be having its own way of reaching that position, and solving that position or getting the joint positions to corresponding to that position cannot be generalized because of the robot configurations. We will see why what the problem is later, but that is the problem here. It cannot be generalized, and unique solutions are rare and multiple solutions exist. So, many times you will be having multiple solutions, that mainly because suppose you have a point here, or okay, assume that this object is here and you want to reach here, this point. So, you can actually reach from here, you can actually reach from here and reach here, or you can actually reach like this also. So, you can actually have a elbow up or elbow down kind of a solution. So, this kind of multiple solutions are very common in inverse. Okay, and because of all these, you have this inverse problem as a very difficult than the forward problem. Okay, so, forward problem was very generalized. For any set robots configuration, we can have a general solution, and therefore, we are not able to we are able to get a generalized solution. But in the case of inverse, this is not possible because of various reasons which we will see later, and unique solutions are not there. So, all this actually leads to the inverse problem as a complex one compared to the forward problem. Okay. So, now if you want to solve this inverse problem, so we can look at what is happening in the forward relationship. So, we have this arm matrix which we discussed in the forward relationship, which represents the position P and orientation of the tool in base coordinate frame as a function of joint variable Q. So, now when we do a forward kinematics, for Q is the joint variable here. So, Q are the set of joint variable, then we can actually represent the position P. So, this position vector P and its orientation of this tool frame can be represented using this rotation matrix and the position vector RQ and PQ. Rotation matrix and the position vector can be used to represent this. Now, what is this P? P is basically the position of this point, position of this point P, and represented in terms of Px, Py and Pz. So, we represent it as Px, Py, Pz, and then we have a relationship. Px is something, Py is something. This is what we get in the forward relationship, and this will be a function of the Q. So, we know that it is a function of Q depending on the type of robot, it may be a function of Q1 to Qn, and this also is a function of Q1 to Qn. Similarly, R also we have this as a vector, I mean 3 by 3 matrix. So, you have the normal, approach and sliding vectors. So, you can call it as Nx, Ny, Nz like that. And each one also we saw that this also is a function of joint variables. So, Nx is equal to a function of joint variables, Ny is a function of joint variables like that. So, we have these equations available with us. Now, the question is how can we actually use Px? Suppose we know Px, how can I find Q1, Q2, Q3? So, we have to start from the forward relationship and then solve this relation to find out the Q. So, that is the requirement in inverse kinematics. So, given the desired position P and orientation R of the tool, find values for the joint variables Q which satisfy the arm equation. So, now if suppose this P is given to you, now you want this P to be reached here, you say that okay, this is the P which I want to reach and I have an orientation like this. If this is known, if this P and this RQ is known, how can I find this Q corresponding to this P and R? That is the inverse problem. So, given a desired position P and orientation R for the tool, find values for the joint variables Q which satisfy the arm equation. So, this is the inverse kinematics problem. Okay, so, if I to represent this relationship between the direct and inverse kinematics, you can see that if you have the joint space parameters Q if you know this q1 to qn, that is we call it as joint space, joint parameter, joint variables. Now, we use the direct kinematics or the forward kinematics to get the tool configuration space Rn, which actually is the P and R, that is the position vector and the rotation matrix can be obtained. So, for any value of q, you will be able to get the position and orientation using the forward kinematics. We call it as the tool configuration space. Now, if you apply this inverse kinematics to this, suppose you have, you know P and R, then you apply inverse kinematics and you get the joint space variables. So, use this tool configuration space information using inverse kinematics, then get the joint space is the inverse problem. So, you can see that if we want to solve the inverse kinematics, we need to have a direct kinematics relationship, because that direct kinematics relationship is the one which is used to solve the inverse kinematics problem, or we need to know the forward relationship of the manipulator to solve the inverse kinematics. The arm matrix should be known to us. Okay. So, now look at the solvability of this relationship. So, as we know, if P and R are known, then we can use some method to solve for Q. So, that is the inverse requirement. Now, see how the P and R are represented. Suppose we have this relationship for the arm matrix, which says that Px, Py, Pz and Nx, Ny, Nz and Sx, Xy, the normal sliding and approach vectors, normal sliding and approach vector, and the position vector is the one which is given to us, because we assume that we know this or this is known to us, and we ought to solve for the joint variables which corresponds to that one. Now, in the case of normal case of forward kinematics, how is it represented? This Px, Py, Pz will be represented like this. For example, I taken one robot configuration, and for that robot we will see that Px is equal to this one and Py is equal to this one and Pz is equal to this one. So, we can see that there can be three equations can be written. For that particular manipulator, we have a relationship that Px is equal to C1 multiplied by something, Py is S1 multiplied by something, and Pz is 215 minus something something. Okay. So, that is the three equations that you can have. Now, similarly, we can write Ax is equal to minus C1 S234, Ay is equal to minus S1 S234, Az is equal to minus C234. So, like this we will see that we can actually get 9 equations from here and 3 equations from here. So, we have totally 9 plus 3, 12 equations from this matrix relationship. So, our matrix is given. So, for Px is equal to this, Py is equal to this, like this we have 9 plus 3, 12 equations. And using this 9 plus 3, 12 equations, we need to find the joint variables q1 to qn. So, you have q1 to qn to be found out, because if Px is given, suppose I have Px is equal to 170 and Py is equal to 50 and Pz is equal to 50. Now, I have to write 170 is equal to this, 50 is equal to this and 50 is equal to this, and solve it to find out what will be the values of theta 1, theta 2 etc., which satisfy this condition. So, that is the way how we need to look at this. So, we have 9 plus 3, 12 equations and n unknowns, n may be 6 or 5 or whatever it is. So, we will see that there are 12 equations and you have n unknowns to solve. So, things seems to be simple, because you have 12 equations and you have only n unknowns. This n will be normally 6 or 5 or whatever it is. So, that seems to be a easy problem to solve. But if you look at closely at this one, you will see that okay, there are 12 equations and unknowns, n unknowns, n equal to 6 for a 6 axis robots. But if you look at closely these 3 equations, we can say Px, Py, Pz, they are independent, because you can actually place the robot in the position, the end effector can be placed anywhere in the XYZ plane within the workspace, so that it can be independent. So, Px, Py, Pz, there is no relationship directly, as long as where you want to place it you can place. So, you can actually get these 3 equations are independent, they have 3 independent equations here, but these 9 equations they are not independent. The reason is that this actually represents 3 vectors. So, this actually represents the normal vector, sliding vector and approach vector, and they are orthogonal, and of course, they are independent vectors. But these 3 out of these nx, ny, nz, they are not independent. Okay, there is a relationship between nx, ny and nz to satisfy this condition of the vector. Okay, so, nx square plus ny square plus nz square is equal to 1. Similarly, sx square plus sy square plus sz square is equal to 1, and ax square plus ay square plus az square is equal to 1. So, that is the unit vector, the 3 orthogonal directions. So, these 3 equations that you are seeing here, these 3 equations are not really independent, and similarly these 3 equations are not independent, these 3 are not independent. So, effectively we have only one equation from here which is independent, and this is only one equation from here and this one equation here. So, we can have only 3 independent equations from the rotation part. This rotation matrix gives you 3 independent equations, though we have 9 equations. Since they are not independent, what we can see is only 3 independent equations. So, these 3 independent equations from this part and then 3 independent equations from the positioning part give you totally 6 equations. So, you can actually get 6 independent equations from the R matrix. So, using the R matrix you will be able to get 6 independent equations to solve for the n variables. So, 6 equations, now we have n variables. So, if the n is equal to 6 or less than 6, we can solve the problem, but when n is equal to 7, you will not be able to solve because you have only 6 equations and 7 unknowns cannot be solved. So, you need to choose one of these, you have to select and then you have to get other 6. So, that actually leads to multiple solutions depending on the values of the first assumption. So, effectively we have only 3 independent equations and 6 independent equations and n unknowns, and nonlinear, they are nonlinear equations and then difficult to solve. So, 6 independent equations and n unknowns and nonlinear equations. So, we need to solve them in order to find out the joint variables, but they are not that easy to solve because they are nonlinear equations, and when n is more than 6, again you will have difficulty. So, that is the difficulty with the inverse kinematics, or that actually tells you the solvability aspect of the inverse problem. We have 6 independent equations and n unknowns, and the relationships what you are seeing here are the nonlinear equations and not that easy to solve. Now, we have to see how to address this problem for manipulators. So, first thing we look at this, is there a solution existing or not. So, we know that there are 6 equations and 6 unknowns. Suppose that 6 n is equal to 6. So, we have 6 equations and 6 unknowns. So, we can actually solve the equations, that is possible, but whether there is a solution existing or not. If there is a solution existing, then only we can solve it. So, if we have to solve using the 6 equations, first thing we need to ensure is that yes, there is a solution existing for it, and therefore start solving it. And how do we ensure that there is a solution existing? So, we look at this, a manipulator is solvable if all the sets of joint variables can be found corresponding to a given n-effector location. So, a location is given to you, and if you can find all the joint angles corresponding to that location, then we call it as a solvable one. That means, you need to get all the sets of joint variables which can actually reach to that position and orientation. So, then if we can find it, then we call it as solvable. Now, there are few conditions under which we can say this is possible. Okay. So, not all positions are solvable, and there are some positions which cannot be solved also. So, first we look at what is the necessary condition to have a solution. That is, if you want to have a solution, what is the minimum condition to be satisfied? What is the necessary condition to be satisfied? The first point is that suppose you have a robot like this, Suppose this is the robot and I will say its workspace is something like this. Okay, I am just roughly mentioning, okay, this is the workspace that the robot is. Now, as a programmer I may not be knowing that what is the workspace it can reach, or what is the all the points I may not be knowing. Suppose I give a position here, maybe it may be possible to solve, but if I say that okay, I want to reach this position, then it is definitely not possible to reach this position, because it is beyond the workspace of the manipulator. So, the necessary condition to have a solution is that it should be within the workspace. Okay, that is, without that condition you can never solve the problem. So, first condition is that the tool point within the workspace. So, the tool point what you want to solve should be within the workspace, that is the first condition. Now, we know that if I want to reach this position, I will be able to reach this position, and if I want to get a particular orientation also. So, I need to have a orientation, desired orientation in a desired position, then I know that there should be 3 degree of freedom for positioning, and I need to have another 3 degree of freedom for orienting. That means, I can get any orientation and any position within the workspace using this 3 plus 3 degree of freedom, that is 6 degree of freedom. Suppose I have only 5 degree of freedom, suppose I do not have, I have only 5 degree of freedom, then it is clear that I will not be able to reach the orientation needed. I can use the first 3 degree of freedom to reach the position, but then I have only now left with only 2 degree of freedom. Out of 5, 3 used for positioning. So, I have only 2 degree of freedom for orientation. That means, I will not be able to get all the orientations, I can control 2 orientation, and the third one will be depending on the 2. So, I cannot really say all the 3 orientations I want and then only have only 5 degrees of freedom, it is not possible, then you will not be able to solve. So, that is the condition if n is greater than or equal 6 to have any arbitrary orientation. So, if I had to have any arbitrary orientation of the tool, I need to have minimum 6 degrees of freedom or more than 6 degrees of freedom. So, if n is equal to 6 or more, then I can have all the arbitrary orientation, and if I have only 5 degrees of freedom, then I say that I need to get all the orientations, it is not possible. That means, I will not be able to solve for any arbitrary orientation if there is only 5 degrees of freedom or number of degrees of freedom is less than 6. So, that is the second condition, necessary condition to have the solution. So, first condition is that the tool point should be within the workspace. The second condition is that n should be 6 if I want all the orientations achieved. Now, another condition is that the tool orientation is such that none of the joint limitations are violated. So, all the robots will be having some physical limitations in joint movement. So, whether your wrist will be having roll, pitch and yaw axis, and each one will be having some joint limits. Okay, so, maybe roll can have all the 360 degree, but pitch and yaw cannot have 360 degree rotation because of the physical limitation. Now, if your orientation says the orientation what you want actually can be achieved if the joint limitations are violated, or we will be getting a solution. But if you say that the joint has limits, then you will not be able to get all the desired orientation. So, we need to ensure that the tool orientation is such that none of the joint limitations are violated. So, in these 3 conditions, these 3 necessary conditions to be satisfied if you want to get a solution, or to have to make the manipulator solvable. Now, that is the necessary condition. So, there are 2 kinds of solutions. So, if you know that this necessary condition is satisfied, then we can actually solve for this. We can solve for the solutions, and the 2 methods of solutions are, one is known as closed form solution and the other one is numerical solution. So, closed form solution is that you can use the algebraic expression or the analytical expression that you already developed using forward kinematics. So, you can use these analytical expressions and solve for it, that is basically known as the closed form solution. So, the analytical method can be used to get a solution, then we call it as a closed form solution. So, analytical method can be either these equations, or you can have a geometrical method also. So, 2 methods are there, either you directly solve these algebraic equations or you go for a geometrical approach and then find out the possible joint angles which will provide the position and orientation. So, that is the closed form solution, and the other one is known as the numerical solution, where you do an iterative search and then find out the solution. So, you start with some value for each joint angle and then search all other joint angles which will actually lead to the desired position and orientation. And if you do a search, and at some point you will find that okay, oh, this meets the requirement. So, that is the numerical methods, which is an iterative and time consuming methods. So, whenever the closed form solution is not possible, we have to go for time consuming method of numerical solution. Similarly, when you have large number of degrees of freedom, you have multiple solutions, then also you may have to go for numerical solutions to get a most feasible solution. So, how do we know whether there is a closed form solution existing or not? That is the second question. So, the first question was that okay, whether it can be solved or not. Now, if it can be solved, which method to be used, whether we go for a closed form solution or a numerical solution. And to get this closed form solution, we call there is a sufficiency condition. We say that there is a sufficiency condition to get a closed form solution. So, any manipulator can be solved for its inverse using closed form methods if it satisfies the conditions given here. That is known as the sufficiency condition. The sufficiency condition says that if 3 adjacent joint axes are intersecting or 3 adjacent joint axes are parallel to one another, then we will be able to solve the inverse kinematics using the closed form methods. And if this condition is not satisfied, then you will not be able to solve it using closed form methods. You need to go for a numerical methods. That is the situation, or that is the condition that says sufficiency condition, where you can solve this using closed form methods. And what does it say? Suppose you have this axis like this, you have one axis here, one axis here, and one axis joint here, and all the joint axes are parallel, then all the adjacent joint axes. Okay. So, all the adjacent joint axes, all the 3 adjacent joint axes are parallel, then you can have a closed form solution. Otherwise, if the 3 adjacent joint axes, suppose you have one axis here and then one axis like this and one axis at this point which actually again intersect these 3. Suppose you have one axis and another axis here which actually like this, then these 3 axes are intersecting. If the 3 adjacent joint axes are intersecting, then you will be having a closed form solution. So, this is the necessary sufficiency condition to get a closed form solution. So, whenever you get a manipulator to be solved for inverse kinematics, first thing you need to check is whether the closed form solution existing or not. If the closed form solution is not existing, then you will not be able to solve it using algebraic or geometric method. You have to go for numerical method only. And from where this condition comes, that you can actually see later when we try to solve. So, probably if you remember the forward kinematic relationship, if there are 3 adjacent joint axes, you might have seen that it actually comes like theta 2 plus theta 3 plus theta 4 format, or we write it as theta 2 3 4. Okay, so, that is the form it was coming in the arm matrix or the arm equation, and that is the reason why we need to have this kind of parallel axis, so that you will be getting it in this format. So, it can actually be solved. If they are not this way, then you will be getting 2 3 and then theta 4 as another one. Then you have to solve for 2 3 and 4 separately. That actually leads to problem in the solution. So, this will be more clear when we try to solve the equations, but the relationship comes from this this condition comes from that relationship developed or that actually happens in the forward kinematics. Similar is the case with the intersection, also intersecting the joint axis. Okay. So, these are the necessary and sufficiency condition for getting the solution. So, necessary condition for existence of solution and sufficiency condition for existence of closed form solution. Okay. And as I mentioned, there will be multiple solutions. So, when it is a redundant robot, so when you have n is equal to 7 or more, then we call it as a redundant robots, because what you need in space is 6 degrees of freedom, and if you have more 7 degrees of freedom or 8 degrees of freedom, controllable degrees of freedom, then it becomes a redundant robot. So, whenever the robot is redundant, then you have multiple solutions, because you can only have 6 only you can solve. So, 7, 8 and all you need to make assumptions, and then for each value of theta 7 or theta 8 you have to find for theta 1 to theta 6. So, that actually leads to large number of multiple solutions. And another one is the elbow up and elbow down solution, which I already mentioned. So, you have an elbow up solution like this. So, you can actually reach this position from here, or you can actually reach the position from here. Okay, this is the elbow up or elbow down solution, that also leads to multiple solutions. Okay, so, always there is no unique solution, you will be most of the time you will be having multiple solution for the inverse problem. Okay, that talks about the basic requirements for the system to be solvable. Now, as I told you, in the closed form solution, algebraic and geometric approach is there. So, the algebraic approach is obtain the equations from the matrix. So, the 12 equation that we already mentioned. So, obtain the matrix equations, the scalar equation from the matrix, and then try to solve them. That is the algebraic approach. Okay. And in this, so this geometric approach we will not be discussing, because geometric approach normally more of a graphical approach. So, you know the position and orientation to be reached, and you know the link length and other orientation other parameters. So, you try to geometrically construct the manipulator position and orientation to see what position of these joints will actually reach the required position, and then find out the joint angles corresponding to that. So, we will not be going to that part, we will be looking only at the algebraic approach. So, here we do this by getting the scalar equations from the matrix form. So, as I mentioned, there will be 12 equations. So, you can actually write down 12 equations using the matrix, that is the R matrix. Now, these 12 equations always in the I mean they are all nonlinear equations, and it consists of trigonometric identity parameters, and therefore, we need to use some tricks to solve them. So, they cannot be solved very easily. There are a lot of difficulties in solving these 12 equations. So, we use some trigonometric identities to combine two equations, first square them and then add them and then eliminate certain variables. So, there are different tricks to be used. For example, you have something like a cos theta plus b sin theta, and then so you can a1 b1 like this, and then probably you can actually, when you add them, cos square theta plus sin square theta will come, and then you will be able to eliminate some of these parameters. That is what actually says. So, such as first square them and add them and eliminate certain variables. So, the trigonometric identities are like sin square theta plus cos square theta is equal to 1. So, such trigonometric identities can be used, and we can actually get them by combining equations. So, you square them, add, and you will get this, and then you can eliminate some of the variables. That is the trick 1 we can use. And another trick to be used is that you use the substitution. So, you can substitute for these trigonometric variables with some other, and then convert them into polynomials. So, the trigonometric equations can be converted to a polynomial and then solve the polynomial. That is another way to solve it. So, for example, you substitute u is equal to tan theta by 2, then cos theta can be written as 1 minus u square by 1 plus u square, and sin theta can be written as 2u by 1 plus u square. And then whenever the cos theta sin theta is coming, you substitute these parameters, these values, and then convert that into a polynomial equation, and then solve the polynomial and then get the theta. So, finally, we need to get the theta. That is the trick 2. And then another trick to be used is that, find out the expression for both sine and cos of a joint angle theta. So, you write sin theta, you find out what is sin theta. Suppose you want to sin theta 1 is equal to k, and then you find out cos theta 1. So, cos theta 1 you write it as square root of 1 minus k square. So, that will be cos theta 1. So, you have sin theta 1 and cos theta 1, and then use a function called a tan 2 to get the theta value. So, a tan 2 cos sin theta cos theta. So, we write it as a function called a tan 2 function. Normal arctan is not used, but instead use a tan 2 function, and that can actually give you a unique expression for theta. So, when you use the normal arctan, so theta can actually be anywhere here, but then when you use an arctan, it will not clearly tell in which quadrant it lies, because arctan value will be the same, but the quadrant will not be specified. But if you use an arctan 2 function, a tan 2 function, you will be able to clearly tell which quadrant it lies. So, you will be able to get the theta value uniquely defined using arctan 2 function. I will explain this when we consider the examples of how to use the arctan 2 function, what is the importance of arctan 2 function in solving these equations. Okay. So, to solve these equations we need to use some of these trigonometric identities or trigonometric tricks, which actually helps us to simplify the equations and then solve them without much of difficulty. Okay, so that is about the method or the way to solve the thing, the inverse problem. So, let us take a very simple example of a 2 degree of freedom planar manipulator. Okay. So, this planar manipulator is given with a link length L1 and a link length L2 we will say, and this one is assume that this one is theta 1 and this one is theta 2. And as I mentioned, the first thing to in order to solve for the inverse kinematics, we need to have the forward kinematics relationship, and that will give you the a matrix. So, we will do the same process. We assign the coordinate from x0, y0, x1, y1, x2, y2, etc., and then see how to get the forward kinematics. So, okay. So, now we need to get this forward relationship. So, I can take this as a px, px1 and okay, this is for so the px is actually this one. So, this is the px and then this is the py. Okay, so, this being a simple 2 degree of freedom planar manipulator, we will be able to write this px and py very easily. So, px can be written as L1 cos theta 1 plus L2 cos theta 1 2. Similarly, py can be written as L1 S1 plus L2 S1 2. Now, we need to solve for theta 1 and theta 2. So, we need to find out for any value of px and py, how can you get theta 1 and theta 2. So, that is the position part. So, we are looking only the positioning part here just to give the feel of how do we solve it. So, theta 1 and theta 2 is to be solved. So, here is equation 1 and this is equation 2. Now, how do we solve for theta 1 and theta 2, because we have only these two equations L1 C1 and L1 L2 C1 2, L1 S1 plus L2 S1 2. So, what we do, we will try to see some of the, we will try to use some of the tricks to solve this. So, one of the tricks is basically to square and add these two equations. So, if I write down as px square plus pi square. So, if I square and add them, then I will be able to write this as like this: px square plus py square is equal to L1 square plus L2 square plus 2L1 L2 C2, because L1 C1 square and L2 L1 S1 square will actually become L1 square, and similarly you get L2 square plus 2L1 L2 C2, and we can get C2 as px square plus py square minus L1 square by L1 square L2 square to L1 L2. So, we have solved for C2. So, once we have C2, we can find out theta 2. We need to find theta 2. So, instead of using directly a cos inverse, we do not use a cos inverse to get theta 2, because that will not tell you in which quadrant the theta lies. because out of 4 quadrants we want to clearly get which quadrant theta is lying, and therefore what we do, we will try to find out S2 from here. So, S2 can be obtained as square plus or minus square root of 1 minus C2 square. So, that is the way how you can get the S2, and once we have S2 and C2, then we get theta 2 as A tan 2 S2 C2. So, this is the way how we can get theta 2, and why we are doing this, because as I mentioned, the function A tan 2 denotes a 4 quadrant version of arctan function. Okay, it allows us to recover angles over the entire range of minus pi to pi. So, it will clearly tell between pi and minus pi what is the value. Okay. And how is it doing this A tan 2 function? So, if suppose it A tan 2 x y. So, if you take A tan 2 x comma y, so it will look at the values of x and y and then decide which quadrant it lies. So, if x and y are 0, then it is indefinite, x is greater than 0, y is equal to 0, then A tan 2 is 0, then x greater than less than 0, less than 0 and y is 0, then A tan 2 is pi, and if y is less than 0, then minus pi A tan 2 0, it lies between 0 and minus pi. If y greater than 0, then it is between pi and 0 and pi. So, this way it clearly tells you which quadrant it lies between 0 and minus pi or minus pi and 0 and pi or 0 and minus pi. So, this way you will be able to get the theta clearly defined within this 4 quadrants. So, that is why we go for A tan 2 function instead of going for a cos inverse or sin inverse or simple A tan function. So, this is the way how we need to get theta 2. So, we will get theta 2 using the A tan 2 function. Okay, so, S2 is plus or minus square root of 1 minus C2 square and theta 2 is A tan 2 S2 C2. And now we can see, because there will be 2 values for S2, you can get 2 values for S2. So, one is for plus and one is minus. Now, you will be getting 2 values for theta 2 also. So, you get theta 2 for one value of S2 and theta 2 for another value of S2. Now, if both the values are actually lying within the joint limits of the manipulator, then you have to take both the values as a solution, and if one is outside the joint limit, then you can eliminate and then proceed to select the find the next joint angle. But if both are in the joint limits, somehow both happens to be in the joint limit, that shows that there can be 2 ways to theta 1 value and theta 2 in this case, and you have to use both the values for solving the next joint angle. So, you will be getting multiple solutions that way. So, that is how do you get the theta 2. Now, you need to solve for theta 1. So, you have to substitute for this Px value, Px L1 C1 plus L2 C1 2, that relationship, and then solve it for the joint angle, next joint angle. Okay, so, we will take a more complex one and then go to the solution. Yeah, this one I just wanted to tell you how do you use the tricks to solve for the joint angle. So, we will look at the solving for theta 1 and other joint, if you have more joint angles, how do you solve. So, we will take more complex problems and then try to solve it. Okay, so, this is the 3 degree of freedom case. So, we assume that there is another joint here which actually projecting out, this manipulator is projecting out from the plane and with the distance d3, and then you have this other joints 1 2 here, joint 1, joint 2, and you have another joint 3. Okay, so, here since it is projecting out and there is no other thing, so the orientation will be given by this. So, always the axis is always vertical. So, you will be having nx sx, ny sy, and 0 0 1 0 0 1 as the orientation matrix. So, the orientation of the tool will be always in this format, nx ny sx sy, and the position will be px py pz. So, px py is the position, this pz is because of the d3 which is projecting up. Now, if you have to solve this problem, we will see. So, first we will assign the coordinate frame x0 y0 x1 y1 and x2 y2, and then the tool tip will be having the final coordinate position x3, which is actually projecting out. So, you can see Pz will be always d3 because it is projecting out and then it is actually rotating. So, it will be d3 distance Pz. So, you can actually find out the parameters here, the dH parameters. So, first we need to solve the forward kinematics. So, to solve the forward kinematics we will find out the parameters A, D, alpha and theta. So, here this L1, L2 is A and D3 is this is 3 and then alpha is 0 because all the joints are axes are parallel and theta is a variable. So, theta 1, theta 2 they are variables. Now, if you write this forward relationship using the transformation matrix, you will be able to find out the forward relationship or the arm matrix. It will be like this. So, your Px will be L1 C1 plus L2 C12 as we saw in the previous case also. Py will be L1 S1 plus L2 S12 and Pz will be D3. So, this will be the position vector for the tool or this coordinate frame position will be given by this relationship L1 C1, L2 S2, L1 S1 plus L2 S12 and D3. Now, the orientation will be given by this the matrix C123 minus S123, S123, C123, 0, 0, 1. Okay. And you have the 3 equations Px, Py, Pz and Nx, Ny, Sx, Sy. So, you have 4 plus 3, 7 equations are there. What you need to solve is theta 1, theta 2 and theta 3. You need to solve for theta 1, theta 2, theta 3. So, you have these 3 equations plus 2 equations here. So, 5 equations are there. So, you can actually solve it easily. And we will write this one relationship now. So, Px we will write Px is equal to this, Py is equal to this, Pz is equal to this and then we will write Nx is equal to C123, Ny is equal to S123 etc. Okay. And similarly Sx is equal to minus S123, Sy is equal to C123. So, this way we will write this relationship and then we will try to solve it. So, as we saw in the previous case also, so Px will be getting L1 C1 plus L2 C12, Py is L1 S1 plus L2 S12. So, if you square and add them you will be able to get theta 2. So, theta 2 can be solved and so theta 2 can be solved using this method and then theta 1, 2, 3 can be solved using this relationship because you have C123 and S123. So, you can actually use that to find out A tan 2 C123 and S123 you will be getting theta 1, 2, 3. So, theta 1, 2, 3 can be solved and theta 2 can be solved in these two. So, theta 2 can be solved directly from here and theta 1, 2, 3 can be solved from here, that we saw how to get theta 2 in the previous case and theta 1, 2, 3 can be easily solved from here. Now, the question is how do you get 1 and 3. Okay. So, these are the relationship you have Nx, Sx, Ny, Sy and Px, Py. So, you have these 6 equations written here. And since Pz is equal to constant we did not write that as a separate equation. Now, squaring and adding 5 and 6 we get theta 2. So, we know C2 can be obtained and by using the same method that we discussed in the previous example we can get theta 2 as A tan 2 S2 C2. So, theta 2 can be obtained. Now, using the other equation we will be able to, so this one I already explained how do you get how do you use A tan to get the theta 2. We can actually solve this 5 and 6 for theta 1. So, now theta 1 is to be solved. So, theta 1 cannot be directly solved. So, we need to have a substitution here. So, what we do? We do a substitution here saying that Px is equal to K1 C1 minus K2 S1 and Py is equal to K1 S1 plus K2 C1 where K1 is equal to L1 plus L2 C2 and K2 is equal to L2 C2. So, we will make a substitution like this K1 is equal to L1 plus L2 C2 and K2 is equal to L2 S2. And when you do this substitution, then we can write Px is equal to K1 C1 minus K2 S1. So, the previous Px equation can be expressed like this because of this substitution. And then we write down, we again substitute K1 is equal to R cos gamma, K2 is equal to R sin gamma, where R is equal to K1 plus K1 square plus K2 square root, and gamma is A tan 2 K2 K1. So, this kind of a substitution is needed in order to solve for S1, because we have this the relationship Px is equal to L1 C1 plus L2 C1 2. So, to solve that one we need to have a substitution like this, and when you do the substitution we will get it as Px by R is equal to cos gamma cos theta 1 minus sin gamma sin theta 1, and Py by R is equal to cos gamma sin theta 1 plus sin gamma theta 1, and from there we can get cos gamma plus theta 1 as Px by R, sin gamma plus theta 1 as Py by R. And since we know gamma, so gamma is actually given as A tan 2 K2 K1, and K2 and K1 are known because K2 is known L2 S2, K1 is L1 plus L2 C2, both are known. We will be able to get gamma, and then we will get cos gamma plus theta 1 as Px by R, and sin gamma plus theta 1 as Py by R, and using these two relationship we will be able to get cos the theta 1 as so gamma plus theta 1 can be obtained as A tan 2 Py by R Px by R, and so A tan 2 is Py by Px, secant R is constant. So, you can write gamma plus theta 1 is A tan 2 Py Px, and therefore, theta 1 is A tan 2 Py Px minus A tan 2 K2 K1. K2 and K1 are known, and therefore, theta 1 can be solved. So, this is the way how we can get theta 1 solved, and once theta 1 is solved, then theta 2 is already solved, and we can get theta 1 2 3. So, theta 1 2 3 can be obtained as A tan 2 Ny Nx as I mentioned, and theta 3 can be obtained as theta 2 1 2 3 minus theta 1 minus theta 2. So, this is the way how we can solve. So, we have solved for theta 2, theta 1 and theta 3 here. So, all the joint angles have been solved for this particular robot. So, this is the way how we solve the inverse kinematics problem for manipulators. So, you may find it a bit difficult that you have to do lot of substitution here. So, how do we know what kind of substitution to be made? And this can actually be solved by can be addressed by a different methods where we do not really solve all these. We will use some standard trigonometric equations and then we can solve it. So, we will discuss that in the next class, how can we use standard methods to solve the inverse kinematics without going for too many substitutions. So, we will discuss that the method of solving in a simple way, and we will see a few more examples in the next class. Okay. Thank you.